So projection formulas for chiral molecules. So configuration of molecule, as you said, it is a three-dimensional structure. So it is not very easy to depict it on a paper. You cannot see three dimension in a two dimension because your paper has got only two axes. You cannot see the third y z axis. So how to visualize your structures, chiral molecules on two dimension? So this were done through a projection formulas. Okay, projection. So there are following four two-dimensional structures are known as projection that have been evolved. So there are four types, that is projection, Fisher's projection, Newman's projection, Sahar's projection, flying wedge projection. So these are the four methods where you can see your three-dimensional structures. There is a way where you can depict your three-dimensional structures on a two-dimensional paper plane. So let's go one by one. So what is the first one? First one is our Fisher's projection formula, that is straight line and a horizontal line. So straight line is away from the viewers. If it is on a horizontal line, it is away from the viewer. The structure, so you see in the dotted lines that your COH and CH2OH, they are away from the plane. That's why that's shown on a dotted lines. Whereas your H and OH, which are towards the viewer, so that's why it is shown on a dark line. So this represents your dark line, and the dotted line represented whether the substituents are towards the viewer or away from the viewer. According to that, you can classify. So which are towards you, that are given by your horizontal line, that is H and OH are an or, which, and the things which are on the, which are away from the viewer, are represented by a vertical line. So COH is on the top and your CH2OH is on the bottom. So this is how you represent in a Fisher's projection formula. So when you rotate the Fisher's projection formula by 180 degree, you get an identical compound. So when there is a rotation of 180 degree about the axis, which is perpendicular to the plane of paper, gives an identical structure. Whereas when the similar rotation is done by an angle of 90, you get an non-identical. This has to be remembered. So if you try to rotate it by 180 degree, you get the identical compounds across an axis. And if the same compound, if you try to rotate it by 90 degree, you get a non-identical. So this is your Fisher's projection. Means towards you with a dark line wedges, it represents on the horizontal line, and the dotted line represents your away from the plane. Now let's go for the second projection formula, that is your Newman's projection formula. So what is this Newman's projection? In Newman's projection, the carbon atom away from the viewer is called as a rare carbon. Let us see in this particular example. Now if you can see the carbon atom, if you see over here, which is away from you, that is out of sight, they are represented by a circle, and the three groups which are attached to it are shown as radiating out from the circumference. That is your rare carbon, that is which is behind. Now next is your group, which is next is your front viewer. So which group is in the front, how to see? So this is represented by a center of the above circle. So the circle which is there behind, center of it you put a dot, and there are four lines radiating from it at an angle of 120. These are the three substitutions which are attached. The front line is shown by a dot, and the line which projects at an angle of 120 degree away from. So this is the way where we show the two carbon atoms which are attached. One is your rare carbon and one is your front carbon. So front carbon is rotated by a center, and the three lines which are projecting out of. So bonds joined to the front carbon intersect at a central dot. So you can see it in this structure. You can see a dot, and the substitutions are radiating from that. So this is how the Newman's projection formula looks. You got the rare carbon as a circle and your front carbon as a dot with three radiating groups coming out of it. Okay. So the bond joined to the rare carbons are showing by emanating from the circumference, that are radiating out from the circumference of the circle. This is how you try to represent. The best way to represent it is through N-butane. So N-butane is what? CH4 C4H10. So CH3 CH2 CH2 CH3. So there are two hydrogens and one methyl group attached to your central front carbon, and there is two CH2 and one methyl attached to your rear carbon. So you show it by a circle, the rear methyl to at 120 degree. Similar to the rear front view, you got a dot and three substituents, that is 2H and 1 methyl. So when the similar group, when the groups are far apart from each other, they are known as staggered configuration. When the two groups come, when the group substituents come close to each other, when the substituents come close to each other, when there is when they come close to each other, when there is a torsional string, then it is known as your eclipsed configuration. It is known as what? Eclipsed configuration. So this is your Newman projection where you have a rear view and a front view. Rear view is shown as a circle with the groups radiating out from the circumference with a bond angle of 120 degrees. And the front one is shown by a dot on the circle, in the center of the circles, and the substitution radiating from that particular dot or the center. So this is your Newman's projection formula, basically used in case of your conformational isomers, to study the conformational isomerism. Okay. Next is your Sahars. So in this case you got circle and but in case of Sahars projection, the bond between the two is shown by a long diagonal line. If you see, there are the two carbons. You can take the example of N-butane, similar to that what you have seen in your Newmans. So you have got two carbons. You have got two carbons which are joined by a long diagonal line. Okay, the bonds linking together the substitution of this carbon are shown by projecting. So these two carbons, so like methyl and hydrogens, are radiating out. The methyl and the carbon, methyl and the hydrogen groups are radiating out from this, similar to that. So when the groups, if you see the staggered configuration, the configuration is complete, the substitutions are far apart. But when you rotate that, when you rotate the carbon-carbon single bond in such a way that the similar groups come close to each other, that is known as your eclipsed formula. Similarly to that you have seen in your Newman's. Due to this happens only due to the free rotation across the carbon-carbon to carbon-carbon single bond, and the change in conformation takes place from staggered to your eclipsed form. So whenever you want to change your configuration from one form to another, we have to convert your staggered into your eclipsed form in your conversion. So I will be telling you later. The next is your flying wedge formula. So this is usually to represent in your enantiomers. So enantiomers are depicted by this particular structure. So they are at the four angles of your tetrahedron. The groups, okay, the groups which are towards you are shown by COH and H in a dotted line. OH and CH, one is front and one is behind, and other two are away from, and the two groups are separated. So flying edge is nothing but similar to your fishes. Only thing is that it is shown in a tetrahedral, where that is shown as a straight line. In case of fissure, it is a straight line, whereas in case of your flying wedge, they are shown as a tetrahedral angle. Okay, they are shown as a tetrahedral angle, and this is how you can see. If you see the two enantiomers, the conformation changes at your OH and H. So there is a change in conformation. Okay, the change in your configuration arrangement in the space. So these are the two isomers of your lactic acid. So these are the four projection formula. Now let's see the conversion. These things are very important for you to know how to convert one projection formula to another projection formula. It is very important to know how to convert one projection formula into another. Let us start first by conversion of your Fisher's projection into your Sahars. So what you see in Fisher's, you got a straight line. Your substitutions are across the vertical line. Okay, you got a horizontal line and the substitutions are on the sides. Okay. So Fisher's compound are converted. How to convert your Fisher's projection into your Sawhorse projection? First, you have to it is in the eclipse by holding the model of the horizontal in such a way that the two groups on the vertical line. So if you see the two groups on the vertical line, okay, COH and OH, okay, COH, the two groups, COH groups that are on the vertical line point above the last numbered carbon atom faces the viewer. So it is on the top, okay, and the other carbons are rotated in angle of 90 so that you get a stagger. So when you convert into an this thing, you first of all you have to see in a staggered, then you have to rotate it to get a staggered stable con. You can rotate it by an angle of 180 degrees so that you get a staggered configuration. Staggered is the most stable configuration. So the groups which are on the top and the bottoms are facing each other. If you can see in the particular structure, your COH and COH on the two carbons, the front carbon and the rear carbons are on the top. If you see in this, your OH and H, if you see OH and H, they are on the left hand side of your two carbons, and your other side also contains OH and the H. So this is your eclipse form. So whenever you want to tell this is the most unstable, eclipse are the most unstable because there will be a lot of it. So you rotate the C2 C3 axis in such a way by an angle of 180 degree so that you get an staggered conf, and the staggered projection formula is one of the most stable because there is least interaction between the groups which are attached to the two carbon atoms. Okay, so first thing you have to look at the two carbons, then see the groups, similar groups on the top, and then locate right hand side, left hand side. So you get your eclipse configuration. So now then after getting the eclipse configuration, then you have to rotate it, okay, in 180 degree angle. So get your Sawhorse formation projection formula, which is the most stable. So this is how you convert an Fisher's projection formula into a Sawhorse projection. Now the next is conversion of your Sawhorse into your Fisher's projection. So what you have to do? So the most stable configuration, what did I say in Sawhorse projection formula, is your staggered configuration. So your similar groups are on the opposite side. Now to convert it into your Fisher's projection, you have to rotate it by 180 degree. And what did we say earlier? When we rotate the structure by 180 degree angle, their compounds are identical in nature. Okay. So when you rotate it, so what happens? Your two methyl groups come, your two methyl groups comes to each other. Your H and Br are on the same side. H and Br are on the same side. So now you convert it. Take the front carbon. H is on the left hand side. Brom is on the right hand side. And your methyl. Go to the second carbon, rear carbon. You see methyl down. Your H is on the right hand side and your bromo is on the left hand side. This is how you can convert your Sawhorse projection formula. You have to first thing is that you have to write it in your stable Gauss formula where the two groups, similar groups are on the opposite side. Then you have to rotate it so that it comes into your eclipse conformation. So when it comes to your eclipse configuration, then you have to see the front carbon and the rear carbon, and then according to the rotation, write CH3, H and bromo. That is in your, if you see, it is in your clockwise direction, and in this place it is in anti. CH3H and there is in anti. So you have to look out for this conformation, and according to that you have to put it. So this is how you convert your Sawhorse projection formula into your Fisher's projection formula. Now the next is conversion of your this is how you do it. So you take another example is given over here. You have to do accordingly. Look out for the frontal carbon and rear carbon. Then you have to draw the structure, then rotate it, and this is how you convert your Newman's into your Sawhorse to Newman and then to Fisher's. You have got this staggered configuration. So you weave it according to that into your Newman's projection formula. And once you do into your Newman's projection, that is your staggered, you convert into your eclipse. And once you get into your eclipsed configuration, then you have to see which groups are near to each other. And according to that front and back carbon, you can write your Fisher's projection formula. Hold it in and vertical, keeping the frontal end towards you. You can write convert your Sauer's to Newman's and then to your Fisher's projection formula. Now, how to convert Fisher to Newman and then to Sauer's configuration? So Fisher, you can, what you should see the frontal and the rear carbon. Look into there. You have to get, in case of that, you have to get an eclipsed conformation. Then you have to rotate it by 180 to get your staggered. Then according to that, then you have to see the front and the back, and you have to connect the two carbons by a diagonal line, and according to the position you have to write it, and thus you will get a staggered Sauer. So this is how you do the conversion from your Fisher, Newman to Sauer's projection formula. The next is conversion of your Fisher's projection into the flying edge. The flying edge, what is this? This is mostly commonly used when you are writing it in your book. So the vertical lines in the Fisher are drawn in the plane. So in the plane, which is that in the, and the in the plane of, and using the lines, so the horizontal lines will project above and below. So the, what you say, the vertical line will be towards you and your horizontal lines will be away from you. So if you see in this particular structure, so which groups are there on the plane? So vertical bonds. Vertical is what? COH and methyl. So they are shown on a dark line. Okay, COH and methyl. Whereas your H and Br, they are shown on a wedge and a dotted line, means that are away from. This is how you can convert your Fisher formula into your flying wedge formula. So the molecule is rotated in such a way that bond should be planar to the, bond should be shown in a plane of the wave going away from the viewer and vertical. So vertical line represents what? The vertical lines. Okay, COH, they are towards you, and your horizontal lines away from, that's shown by a dotted line. Okay, so this is how you can convert your Fishers into your wedge formula. So now the most important thing in Fisher's configuration. So you said horizontal line and vertical, you know what does it mean? Towards you and away from you. Your solid lines, wedges represented towards you, and your dotted wedge line represents away from you. Okay, now let's see the tartaric acid. Now see the, lactic acid. You got COH, CH3, OH and H, 4 different groups. Now how do you convert? So in one particular configuration, if you see, your H and OH comes on your horizontal, and COH and CH3, they come on your vertical line, that is towards you. This is how you can depict. You have to convert into it. Now if you go for R and S, it exactly becomes opposite. Your configuration exactly becomes opposite. The OH which is on the right hand side comes to your left hand side. So that's very much important where the OH is there. See, OH, if it is on the right hand side, it is shown on the right hand. If it is on the left hand side, it is shown on the left hand side in your Fisher's wedge formula, and how it is converted into your Fisher's projection. Now what are allowed in your Fisher's projection formula? As I had earlier said, if you rotate along the axis by 180 degree, your R configuration will always remain R. If you can see the structure, methyl goes up, COH goes, but still your configuration remains the same. Still the configuration remains the same. So if you convert from R, if you have got an R configuration, and if you try to rotate it by 180 degree, means two groups flip. The two groups flip their ends. the lower group goes top and the uh, higher lower group goes on the top and the right hand side goes to the left. When there is a 180-degree rotation, the configuration remains the same. Now let us see the example. Now this is R, OH, COH and CH3. So it is in an, it is R. Now this, whenever you try to change the configuration, still the configuration remains the same. But when you rotate it by 90 degrees, so when you rotate it only 2 by 92 substitution, your COH comes to down and CH3 goes up and OH goes up. So if you just rotate it by 90 degree, the configuration completely changes and it is not allowed. 90-degree rotation of your compound is not allowed in stereochemistry. It is illegal. You will get a change in configuration. So if one group is held steady and other 3 groups are rotated clockwise and clockwise. So what happens if you see, you hold one group and change the position of other, still the configuration is retained. So if you hold one group constant and rotate the other 3 groups in a clockwise or anti-clockwise direction, still the configuration remains the same. So that is allowed. One group kept constant and other 3 groups you change the position, still the configuration is maintained. So this is very important. So what is allowed, what is not allowed? 180-degree rotation allowed, 90 degrees rotation not allowed. You keep one position constant and rotate the other 3. You in a clockwise and anti-clockwise direction, the configuration remains the same. The configuration remains the same. So this is very much important in your stereo. So let's now look into the physical properties of stereoisomer, that is optical activity. The physical and chemical properties of the two enantiomers, as we explained earlier, are identical except their interaction with your chiral compound. So only difference is what happens when they react with the chiral compound to form a diastereomer. So that is the only difference. Rest all their physical properties and chemical properties are identical of the two enantiomers. They have identical physical except how they rotate the plane polarized light. Very important. So all the melting point, boiling point, everything is same, but only thing they differ is the how they interact with the plane polarized light. The plane polarized light is a light that oscillates in a single plane. So when all the rays of your lights oscillate in a single plane, they are parallel to each other in a single plane, such type of light are called as your plane polarized light. It is known as plane polarized light or polarized light. The plane polarized light arises by passing the ordinary light through a nickel prism, that is your polarizer. So when you pass your ordinary light through a plane nickel prism or a polarizer, whichever is going in all the direction, it will be made to oscillate in a single plane, that is parallel to it. So these are known as polarizer. And a polarimeter is an instrument that is used that allows the plane polarized light to travel through a sample tube containing an organic, and it permits the measurement of the degree to which the organic compound rotates the plane. So with the help of a polarimeter, you can measure how much the compound rotates the plane polarized light. Okay. So with chiral compounds, the plane through an angle of, as we said, it rotates through an angle of alpha. Okay, and the angle alpha is the measure in degrees, and it is called as observed rotation. So whatever observation we get when you read through the plane polarized light that gets deviated, that is known as observed rotation. And the compound that rotates the plane polarized light is said to be optically active. So the criteria for compound to be optically active means it should rotate the plane polarized light. Okay. Now see, this is a diagram of your polarimeter. So there is a source, ordinary light, which directs in all direction. It passes through a polarizer, that is a nickel prism or something. So when the moment it passes through that, they oscillate in a single plane, because it gets converted into a plane polarized light. Now this light passes through your sample tube, which contains a chiral compound, and these chiral compounds rotate the rotate the plane polarized light, and that rotation is measured by the analyzer. So you rotate the analyzer and you measure the degree of your deviation. Okay, you measure the degree of deviation of your plane polarized light. This is how you try to measure the degree of deviation, that is rotation. So now let us see what is the rotation of plane polarized light. Can be in a clockwise or anti-clockwise direction. So it can rotate in clockwise, that is toward right side, or it can rotate to the left hand side. Both the ways, according to the enantiomers, it can rotate the plane polarized light. Now, if the rotation of light, plane polarized light, is in clockwise direction, if the rotation of the plane polarized light by the compound is in clockwise direction, then the compound is said to be dextro-rotatory. So if it rotates towards in clockwise or towards right, then the compound is said to be dextro-rotatory, and it is labeled as D, small d. Dextro-rotatory is labeled, it is denominated by small d or cap plus sign in bracket. In bracket plus. Now the second part. So some of the compounds may rotate in anti-clockwise direction. So the rotation, if the rotation is in counterclockwise or anti-clockwise or towards the left hand side, the compound is said to be levorotatory. The compound is said to be levorotatory, and the rotation is labeled by small l or a negative sign. So negative sign or a small l represents your levorotatory compounds. Do not get confused between the capital L and the capital D in case of DL relative configuration. Remember this thing, very important. It represents small d and small l represents the rotation of your plane polarized. If it is towards the right or clockwise direction, it is known as dextro, small d or plus. If it rotates in counterclockwise direction, it is known as minus or L, small l, that is known as levorotatory. Okay, the enantiomers that rotate the plane of flow in equal extent but in opposite direction. So you know that if one enantiomer rotates in right hand side, the other enantiomer of it will rotate in the left hand. So if one is D, the other enantiomers will be L rotatory. Okay, levorotatory. Thus, if an enantiomer head rotates the plane polarized light to plus 5 degree, then the same concentration of the enantiomer B rotates at minus 5. So both the enantiomers A and B, which are mirror images of each other, rotate. If they are in equal concentration, they will rotate in exactly opposite direction, equal amount, but in exactly opposite direction. So this is how you try to differentiate between the two enantiomers. There is no relation between R and S with prefix plus and minus. So your absolute configuration has no relation with your rotation. Your R can be positive or negative. It can rotate the plane of polarized light in the left or right. So there is no relations between your prefix R, capital R and S, that is absolute configuration, with the rotation of your plane polarized light. Okay, there is no relation between your optical relation and your configuration. Keep this thing in mind, very much important. Now, what is specific rotation? Now, that is observed. Alpha is your observed rotation. Now, the definition of specific, it is the number of degree of rotation. It is degree, that is alpha. If 1 decimeter, that is 10 centimeter long tube is used and the compound being examined is present at the concentration of 1 gram per ml. So it is the degree of rotation observed. So it is the degree of rotation observed when a sample tube of 10 centimeter or 1 decimeter long tube is used, and the compound that is exam is in the concentration of 1 gram per ml. So such type of rotation, the observed rotation in such a condition is known as specific rotation. It is known as specific rotation. So what is specific rotation? It is the number of degree of rotation observed if 1 decimeter, that is 10 centimeter long tube, is used and the compound being examined is present at a concentration of 1 gram per ml. Very important. This is usually calculated from the observations with the tubes of other lengths and different by means of this equation. So specific, if you want to keep it in different concentration, we can also do it, but we have to put it into this particular. So what is specific rotation? That is denoted by alpha in square bracket. What is alpha? Degree of rotation. And if it is written in square bracket, okay, close bracket, then it is known as specific rotation, and it is given by the formula alpha divided by L into C, where alpha is the observed rotation, L is the length of the sample tube in decimeter, and C is the concentration in grams. So what concentration you are using, what length of the tube you are using, and you check the observed rotation, you can put it in this equation to get your specific rotation of your chiral compound. Okay. Now, what does this specific rotation depends upon? It depends upon the nature of the substance, concentration of the nature means whether it is dextro or levorotatory, concentration, length of the polarimeter tube, and the wavelength of the incident monochrome. Usually 598 nanomolar wavelength is used for your observation, and the temperature, because temperature plays a very important role. Temperature can change the conformation. So these are the 5 criteria on which the specific rotation depends. So the 5 criteria are nature of the substance, concentration of the solution in gram per ml, length of the polarimeter tube, wavelength of the incident monochromatic light, and the temperature of your sample. Okay, these are the conditions which are necessary to observe the specific rotation, to calculate the specific rotation. Now, some other physical of our optical purity. Now let's see what is enantiomeric excess. What is enantiomeric? It is used to measure the optical purity of the compound. It is measured. It is used as a measure how much one enantiomer is present in excess of the other in an enantiomeric. So there will be, in a racemic mixture, there will be both the enantiomers, A and B. So how much is the concentration of one enantiomer in that racemic mixture in comparison to the other can be found out by the term called enantiomeric excess, and it is denoted by EE. Enantiomeric is denoted by EE, and it is given by one of the formula, percentage of one enantiomer minus the percentage of another enantiomer. You know the percentage of one enantiomer, you know the percentage of another enantiomer, you can find the enantiomeric excess. That is the purity of your optical purity of your sample. Now let us consider an example. So from the example, it was found that the mixture contains, the racemic mixture contains, racemic mixture means both the enantiomers are present. So the mixture contains 75% of one enantiomer and 25% of another enantiomer. So what is the enantiomeric excess in this case? 75 minus 25, that is 50%. So that is your enantiomer. Thus there is 50% excess of one enantiomer over other in an reaction mix. Means one enantiomer is present 50% more than another. This is how you try to find out the enantiomeric excess. There is one more method where you can calculate it. There is one more method where you can calculate the enantiomeric excess. This is how can you calculate. You have to know the specific rotation of the mixture. First thing what you have to know the specific rotation of the mixture, and if you know the specific rotation of your pure enantiomer, then you put the enantiomeric excess can be calculated by the formula enantiomeric excess is equal to specific rotation of the mixture divided by the specific rotation of the pure compound, pure enantiomer into 100. So you got the specific rotation of the mixture, you got the specific rotation of your pure compound if you know, then you can find the enantiomeric axis of your specific rotation of your compound will be specific. You can find it out. It is standard. And if you by calculating the specific rotation of the mixture, you put it in this particular formula, you will come to know the enantiomeric axis. In short, you will come to know how pure your compound enantiomers are there in your mixture. So let us take one example. So optical purity or enantiomeric axis can be observed rotation, specific observed specific rotation divided by specific rotation of pure. That is the, and if you multiply it by 100, it will give your optical purity. So sample of 2-bromo observed was 9.20 and the pure sample it was 23. So you take, that is 0.4. 0.4 into 100, that is 40%. So your, this means that one of the enantiomer is present 40% more than the other. Okay, so the other mixture concentration will be 60%. So total number of amount of enantiomeric in the mixture will be 40 plus 60 divided by 2. That is your 70%. Okay, this will be the concentration. This will be the concentration. So one enantiomer will be present in 70% and other enantiomer will be present in 30%. This is how you can calculate the enantiomeric purity or enantiomeric axis. Okay. Now the physical now continuation of physical properties of steriomer, the racemic mixtures. So what are racemic mixtures? Equal amount of two enantiomer is called racemic mixture. Okay, it is known as racemic mixture. If there are unequal, they are known as racemic mixture. And racemic mixtures are optically inactive. The racemic mixtures are optically inactive because two enantiomer rotate the plane of polarized light in equal direction but in opposite direction. So they cancel each other. So there is no, so if you mix two enantiomers together, you get a racemic mixture and the observed rotation will be 0 if it is in equal ratio. Now let us see the properties. Enantiomer A melting point is same as that of your B. Boiling point is same, but in comparison with this, equal in magnitude but in opposite. B also same, only thing opposite. But in the case of racemic may be different from A and B, and the observed rotation will be, melting point may be different, but observed rotations will be 0. Okay, just give me. Okay, this is the properties of a racemic mixture. Now what is the next topic is racemic modification and resolution of racemic modification. What is racemic modification? Racemic mixture is a mixture of two equal amounts of both the enantiomers. Hence they are optically active. Racemic modification is nothing but equimolar mixture of a pair of enantiomers. These definitions are very important. Okay, racemic mixture or racemic modification is nothing but equimolar mixture of a pair of enantiomers. Okay, it contains both the enantiomers in equal concentration. They are known as racemic modification. And racemization is nothing but a process of converting an optically active into racemic modification. That is conversion of an optically active into its two enantiomers in equal concentration. That is known as racemization. So what is racemic mixture or racemic what is racemic mixture or racemic modification? It is nothing but equimolar mixture of both the pairs of enantiomers. And racemization is a process of converting an optically active compound into its racemic modification or a racemic mixture. So these definitions are very much important. Okay. Now different methods for racemic modification. Different methods for racemic modification. How to convert an optically compound into an racemic mixture. What is the mixing? The best method is to mix equal proportions, equimolar proportion of both the physical mixing. Next is synthesis of chiral compound from a chiral compound. You cut and let's take an example of prochloride. If you got an carbonyl compound, okay, got a carbonyl compound, you react it with to form an alcohol. So when you convert an carbonyl which does not contain a stereogenic center, when it gets converted into an alcohol, you get a stereogenic center. So there may be two possible configuration. There may be two possible configuration that can be attained. So this is how you prepare a racemic mixture from a chiral substance, because your carbonyl group will not be a, because it is sp2 hybridized carbon, so it will not be a stereogenic center. But when you convert into an sp3 hybridized carbon, that is your alcohol, primary alcohol or a secondary or a tertiary alcohol, it becomes a sp3 hybridized carbon. So thus you can convert an achiral compound into a chiral. Racemization under the influence of light, heat and chemical reagents. So you can use different chemical reagents to convert your optically active compound into an optically inactive, that is your racemic. So these are the three methods for preparation of your racemic modification. The next topic is chiral resolution. Please mention, it's the most important topic, chiral resolution. Now what is chiral resolution? What is chiral resolution? In stereochemistry, it's a process for separation of racemic compounds into its pure. Racemic modification is conversion of an optically active compound into its racemic mixture, but chiral resolution is exactly opposite. What it is? It is a process of separation of racemic compounds, that is racemic modification, into its pure enantiomer. So from the racemic mixture, you try to separate out each of the enantiomer. This process is known as chiral resolution. This process is known as chiral resolution, and is the most important tool in production of optically active compound, optically active and pure drugs or compounds. So chiral resolution is a chemistry, is a process in stereochem, it's a process for separation of racemic compounds into its pure enantiomers. Okay, into its pure enantiomers. Now let's see the methods for resolution of a racemic modification or a racemic mixture. First is your mechanical separation, second is your seeding method, third is your biochemical method, fourth is your chemical method, fifth is your kinetic method, and sixth is your chromatographic method. Now let's go one by one. What's the first thing? Mechanical separation. So what is this mechanical? Use tweezers and all. Initially they used to see the different isomers because they'll have different structures. So according to that crystal structures, they will try to separate it. Difference in the crystal structure will be observed, and they are handpicked using your microscope. They'll be handpicked using magnifying lenses or microscope. So example is crystals of ammonium, racemic ammonium citrate. Okay, so can be separated using this method. Next is your seeding method. What is this seeding method? We have studied in recrystallization process. So what do? You put a pure compound inside that. You put a pure compound in a mixture. So what it will do? It will separate out the pure, the form which is with which it is associated. Okay. So what happens? So first you have to prepare a supersaturated solution of a racemic mixture. Yes, it's the first part in your recrystallization. Then add crystal of one enantiomer, pure enantiomer, as a seed. So that will initiate your seeding. So it will group your similar enantiomer across it, and that will help to recrystallize out that particular enantiomer. So that particular enantiomer will come out from the racemic mixture, and it will be in a pure form. So this is known as seeding method, where you put one pure enantiomer into that compound, into that mixture, supersaturated mixture, that will recrystallize your one enantiomer from the racemic mixture. That is the seeding method. That is your seeding method. Now let's go for the third. So first one is mechanical, using tweezers. You check because of the change in your crystal structures. You can see it on the microscope and you can separate it. That's mechanical. One is seeding. You put your pure enantiomer into a racemic, supersaturated racemic mixture. So your one of the enantiomers separates out. That's one of the method. Now third is biochemical. So what do you mean by biochemical? Biochemical means you use microorganisms. It's a process where one of the enantiomer is destroyed. In biochemical process, one of the enantiomer is completely destroyed. Why? Because micro absorbs one of the enantiomers. So it will take away one of the electrons, enantiomers, and leaving out other enantiomers like plus or minus. In case of, let us take an example of penicillin glaucum is added to ammonium tartrate. It is added to a racemic mixture of ammonium tartrate. What does this penicillin glaucum do? It will decompose the D form, dextro form of this thing. Your dextro form of your ammonium tartrate is completely used up by your penicillin glaucum, and left is what? Only your levo form. Your levo form is unaffected, and this can be separated out from the mixture. This can be removed. So the main drawback of this thing is that half of the material gets destroyed, it gets consumed by the micro, and half is retained. So you should know, if you the specific one, if you know which one you have to isolate, then you can use this biochemical method. It's a slow process and only small amount can be separated. So this is the drawback. So in case of biochemical method, it is a destructive method where one of your enantiomer is completely used up. It gets completely used up, and you use microorganisms for your separation. Example, penicillin glaucum used for separation of your ammonium tartrate from racemic mixture, where D isomer is completely used and L is left. L is left. Your L isomer is left. Okay, unaffected. This is how you can separate. Now the fourth is what? Chemical method. Now fourth is what? Chemical. This is the best and practically used method. This is the best and practically used method. So what do you do in this thing? The racemic mixture is converted into a diastereomer by reacting with an optically active compounds. Okay, separate the diastereomers, thus you obtain a pure chemical. This is through various chemicals. So what is the, and we have studied enantiomers have got same physical and chemical properties, but diastereomers have different physical and chemical properties. This can be used for the separation. They can be used by fractional distillation, fractional crystallization, or crystallization process. The diastereomers can be easily separated. So what you do, you convert your enantiomers, racemic mixture, into an diastereomer by reacting with an optically active reagent. Then you separate the diastereomer that is formed because of the difference in their physical and physical properties. Use any distillation crystallization method to separate the two in a diastereomers, and then again reobtain your enantiomers by using various chemical reactions. Now let's go for an example. Okay, let us take a racemic mixture of an acid. You take an racemic mixture of an acid, you treat it with an pure enantiomer, that is amine. So when you treat it with an amine, you get a diastereomeric salt. You get a amines reacts with your acid to form an amide. You get both the things. Now these reactions and this salt that is formed, they are not enantiomer, but they are diastereomer, and diastereomers can be separated. Various techniques like recrystallization. And once these diastereomers are separated, you get two different diastereomers separated. Then you do treat it with your strong base. When you do treat it with the strong base, the amide bond which is formed hydrolyzes, and you get your pure enantiomer. You get your pure enantiomers can be separated. So this is how you can use a chemical method for separation, and this is what is used in industry for separation of your racemic mixture. Used for the separation of your racemic mixture. Now the kinetic method. So what is kinetics? Kinetics means rate of reaction. Kinetic means rate of reactions. So in the reaction, the chiral reaction partners or a catalyst, enantiomer specific, displaces different. So there are catalysts which are present. There are various chiral reagents which are present. The enantiomers will react with it in a different rate. So this can be used for the separation. How they react in presence of that catalyst. One enantiomer will react fast, other will react slow. The product which is formed can be separated, and thus you can separate your enantiomer depending upon the rates of the reaction. But only criteria which is necessary is that there should be a large enough difference in the rate of reaction. Then only it is possible. Then only this it is possible. So if you can see starting material 1 R and S chiral reagent, the product and your starting material can be separated. Okay, this is how you do the separation using kinetic method. And the last one is chromatographic method. The last one is that is selective absorption method. It is known as, it is using a column, HPLC gas and all can be used, where it has got an active absorbent in the column. So your reagents get attracted, one enantiomer gets attracted and other gas. So this is how you use. Absorbents like starch, sugar, quartz, etc. are used. Techniques are gas chromatography, HPLC, thin layer chromatography and column chromatography used for the separation of your racemic mixture. For the separation of your racemic mixture. Okay. Now elements of symmetry. See, what are these elements of symmetry? So as you have said, compounds though it contains stereogenic centers are said to be achiral. Why they become achiral? This is one of the reasons. Elements of symmetry. If any one of these elements of symmetry is present in your molecule in a compound, chiral compound, then the compound becomes achiral. Now let's see what is elementary. Molecules that are achiral or stereogenic in nature form non-superimposed mirror images and are asymmetrical as a whole image, and they would deflect the plane of light. So a normal chiral or a stereogenic molecule will have all these criteria. It will form a non-superimposed, it will be asymmetric, and it will rotate the plane of plane polarized. But molecules forming superimposable mirror images means they overlap each other on their mirror images are symmetrical images. Why? Because they are symmetrical in nature and do not deflect the plane polarized light. These molecules are said to be optically inactive. These molecules are said to be optically inactive. This symmetrical molecule possesses any one of this element of symmetry. So there might be any one of this element of symmetry within this molecule, so that they are superimposable on their mirror images and they do not rotate the plane of polarity. Now let's go one by one. First is plane of symmetry. What is plane of symmetry? Plane of symmetry is defined as that element of symmetry in which the molecule is divided into two equal halves. In which the molecule is divided into two equal halves. One half is the mirror image of the another half. So you can slice the molecule such that your upper part of the molecule is exactly the mirror image of your lower half. Due to this presence of mirror images forms within the molecule, the total deflection of plane polarized light is zero. So when there are mirror images of each other within the molecule, then the total rotation of plane polarized light is zero. This molecule exhibits optical inactivity. These molecules exhibit optical inactivity, and this optical inactivity exhibited due to an inherent property of the molecule, because this property is within the molecule. This is an inherent property of the molecule. Thus the molecule is said to show optical inactivity due to internal compensation. Because of the internal they have plane of symmetry within the molecule. Examples: mesoform of tartaric acid. So if you see tartaric acid over here, COH, your first carbon contains COH, OH and H. On the OH on the right, H on the left. You look out for the second stereogenic cell. It also contains COH, OH and H. OH is on right, H is on the left. So if you try to draw a line in between the two, this compound contains an an inherent internal property, that is they are mirror images of each other. They contain a plane of symmetry between the two chiral atoms. That's why they are said to be achiral. So this particular symmetry is known as element of symmetry is known as plane of. It is an internal compensation. It is internal because of the internal plane of symmetry. They are mirror images. Now let's go for the next, center of symmetry. What do you mean by center of symmetry? The center of symmetry is the element of symmetry in which a line, just see in the structure, when you draw a line from any group of a molecule, passing through the center of the molecule. You take a draw from the center of molecule and meets an identical group extended to be at an equidistance from the center point. So you draw a line from diagonally from one point to another, and if you have got the same group which are equidistant from the center point, okay, which are equidistant. Example, you take the particular example 1,4-dimethyl cyclohexane. You got a methyl group at the first position and a methyl group at the fourth position, and they are, when you draw a line, they are equidistant from the center. Imaginary line, when you draw from the center, these two substituents are equidistant from the center and they are connect to each other diagonally. So such type of symmetry, if their molecule show, then they are said to have a center of symmetry and the molecule is said to be a chiral, and the two substituents are equidistant from the center point. Okay, this is an example of 1,4-dimethyl cyclohexane center. Now second example is your 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid. This is the entire molecule. You see at this compound, you draw COH and COH. You draw a diagonal line coming from the center. The COH meet each other. From methyl and methyl, when you draw a center joining each other, they meet each other. Okay, when you draw diagonally, and they are equidistant from the center because it is a square. Cyclobutane is a square. It is square. So they are equidistant from the center. So such type of molecule try to possess center of symmetry, and the molecule is said to be optically inactive because of center of symmetry. Now let's come to the next, axis of symmetry. Next is axis of symmetry. What do you mean by axis? You got a central axis is nothing but a central line which is equidistant from the four corners of your molecule, central portion. Okay, a molecule which possesses an axis of symmetry, if rotating a molecule by a certain angle around the axis. So you got an XY axis, you got this particular molecule, that is 1, 2, 3, 4 tetra methyl cyclobutane. Okay, when you try to rotate the molecule around the axis, okay, you, as is passing through, results in an arrangement similar to the arrangement before the rotation. So when you try to rotate this molecule, if you see, however you try to rotation by any angle, like 90 degrees, you get the same orientation. You get the same orientation. You can see the structure 3 and 4. If you try to rotate it, you get the same orientation. The rotation of the molecule by an angle of 90 across the axis passes through the center of the molecule perpendicular, results in the same structure. Okay, so such type of compound are said to possess axis of symmetry, and if such compounds possess axis of symmetry, then the molecule is said to be a chiral. The molecule is said to be